So the final topic in Year 11 chemistry is called chemical analysis. This topic isn't so much about chemical reactions, more about how substances behave and how we can define them and how we can separate different substances from each other, and also a few ways of testing for substances. It's divided into three main sections, the first of which is to look at pure and impure substances. So the words pure and impure can be used in chemistry to describe certain arrangements of substances. So if we look at these examples kind of drawn out as sketches, so we've got three different containers here. In the left container we've got just one type of particle by itself. So we said this is one element in the box and it's not mixed with anything else. In the second box we've got two different elements because one's white, one's black, but they're joined together. That would make a compound, and importantly there is only one type of compound or one substance in this box as well. These first two boxes, even though one is an element, one's a compound, you'll see that they only contain one type of substance. So in other words, we've only got white circles in this box, and this box we've only got this combination of white joined to black. There's not a mixture of different types here. So these two boxes are examples of pure substances. So a pure substance would be a single element, in this case, or a single compound, in this case, not mixed with any other substance. The opposite obviously is an impure substance. That's what we see in this final box. Here we've got three atoms of an element, but it's not just the element by itself, it's mixed with one molecule of a compound. So in other words, there's more than one substance in this box. You've got element and a compound together, they're not the same, therefore it's impure. And the way we'd normally define an impure substance is as a mixture of more than one substance joined together, but not chemically. So mixture is two or more substances mixed together, which are usually easy to separate. So now we've got an idea of the difference between a pure substance, an element or compound just by itself, or an impure substance, a mixture of more than one substance put together. We need to know how any differences in their behaviour. And one key difference between pure and impure substances is behaviour on their melting point. So first of all, the melting point is just the temperature at which a solid changes into a liquid. So if I was to take a substance and try to melt it by heating it up, and if I kept track of how the temperature changed over the course of that melting process, I would get a graph that looks something like this. So as I supply more and more heat to the substance, the temperature should increase. When I got a pure substance, say it's starting as a solid, as I heat up that solid, the temperature of the solid is going to increase. If I reach the melting point of that solid, it's going to turn into a liquid. And what we see in this graph is it actually causes the graph to go horizontal, as all of the heat energy being put into that substance is going into making it melt, not actually making the solid get any hotter. Once the substance is entirely melted, it now goes up to being a liquid, and the liquid's temperature can increase as the heat is still supplied. So the key bit is, as you change state from solid into liquid, or indeed liquid into gas, you get a little horizontal section where the temperature doesn't increase anymore because all the heat you're supplying to that substance is going into melting it. That's for a pure substance. You expect to see a very sharp point where it goes horizontal at the melting point of the substance. The difference we see is when we've got an impure substance. And there are exactly two differences you need to know about for impure substances in terms of this graph. If we start off as solid but now it's impure, the temperature will still increase as normal as you start heating it, but when it gets towards the melting point, two things are different. First thing is that it starts to melt a little bit sooner than the pure substance. And the other thing is that it doesn't actually melt over a sharp temperature. So where we had this nice horizontal section for the pure substance, this impure substance is melting over a range of temperatures. It's not a horizontal line, it's kind of going up a little bit. So it's both lower and more spread out. So that's what we've got for impure substances. So if you ever wanted to lower the melting point of a pure substance, you would add an impurity to it. The last little thing on mixtures is a key use of mixtures, which is known as making a formulation. Now, formulation's got quite a long definition you need to learn off. So a formulation is a mixture that's been designed as a useful product and is formed by mixing together several different substances in carefully measured quantities to ensure the product has the required properties that you need. In a nutshell, it's basically saying it's a mixture you make with a purpose. So in other words, it's a carefully constructed mixture with a particular purpose in mind that's made in very specific quantities of different substances to get your desired kind of behaviour. A few examples to know about that, you could have metal alloys, medicines, or fertilizers will all be accepted in the exam. Just to pick on one to maybe explain the point a wee bit further, if you think about Calpol being an example of medicine, it's a mixture of paracetamol, which is painkiller, so that part of it's got purpose, but it's also for children. Paracetamol is quite bitter, so you add sweetener to it to make it more palatable or easy to eat. So you got two different things in that mixture. You got sweetener, you got Calpol. They got very specific quantities to be added together to get a very specific outcome to your product at the end. So it's a useful mixture is what formulation is. The second section of the topic is on something called separating techniques. So this is the idea that you might have an impure substance, so in other words, two or more different things mixed together, that you might want to get separated from each other. And there's 6 different techniques you have to look at for different scenarios of different types of substances you might want to separate from one another. So look at each one in turn. So you would use filtration if you're trying to separate an insoluble solid from a liquid. A good example of that would be if you had sand mixed with water. Now the sand does not dissolve in the water, but you want to be able to get it out quite easily. The solution that is filtration. You have a conical flask or any kind of beaker or evaporating dish. You have a filter funnel and it contains filter paper inside it. The solid that's not dissolved will remain in the filter paper. It's known as being the residue. And the liquid that you got left behind goes through the filter paper and goes down into the flask. It's known as the filtrate. The next technique is called evaporation. That's when you're trying to separate a solute from a solution. Now, solute is just a word to describe a solid that can dissolve in water or dissolve in a particular liquid. So think of a more kind of easy to understand example. If you had salt dissolved in water, it's a solution of salty water, and you might want to get the salt back. So obviously we can't use filtration for that one because the salt's already dissolved, so they should end up both going through the filter. What we use instead is evaporation. When we put on a tripod, a gauze, and evaporating dish above a Bunsen burner, it'll heat up the solution, the water will evaporate, and what will be left behind is your solute. So in this case, we're talking about the salt. And it gets the water separated from the solute, which is left behind. If you did the same technique a little bit more slowly, if you end up with a saturated solution and that gradually cooled down over time, you would get bigger crystals being formed, which is known as the process of crystallization. The third separating technique is a little bit different. It's when we've got two immiscible liquids. Now the word immiscible means doesn't mix. So it's two liquids that don't kind of mix with each other. An everyday example of that would be if you took oil from your kitchen and water from the tap into the same glass, you'll form two different layers. So if we want to get them separated from each other, we use a contraption called a separating funnel. It's basically a big container which has a tap at the bottom and allows you to drain out liquids from the bottom of the container. So if we have, example, oil and water in this container, if we open the tap over a beaker, we can let the bottom layer drain out, and then just before it goes into the top layer, you can stop the tap, switch your beaker to another one, and then drain out the top layer separately. So it's an easy way to get two liquids that aren't mixing into separate containers and therefore separate them. The fourth technique is known as distillation and looks a little bit more complicated. This is where you want to separate a solvent from a solution. So think of an everyday example of that. Similarly to we had over here, if we had salt dissolved in water, in this scenario we're not too interested in the salt being left behind, but we want to keep the water. So obviously in evaporation the water just evaporates off into the room. In this case we want to trap it and keep it. So it's the same kind of mixture, we're just trying to keep a different part of it. So the solution here is we still have a container, we still want to evaporate off the solvent, so heat it up with a Bunsen burner. But we're chopping it in this apparatus. It goes up as a gas through the apparatus. This is a thermometer here to tell the temperature at which it's being boiled off at. And then it goes into this part of the apparatus called the condenser. So on this condenser we've got a tube with a jacket around it which has water running through it from a tap, so cold water goes in at the bottom and out through the top, and that provides a nice cold surface to cool down the steam or the gas and turn it back into a liquid which sort of trickles out at the bottom there. So the water starts off here as a solution but ends up out here as pure water, and the salt in this case is left behind. The liquid that comes out the other end is known as the distillate. The fifth technique is similar, it's known as fractional distillation. Looks very similar to normal distillation, but in this case we're trying to separate two liquids from each other, but they actually are miscible. So obviously we're separating from them with two immiscible liquids that are in two different layers. In this case we've got two liquids which are fully mixed together. So if you think about mixing alcohol and water together, you'll look just the same, everything be mixed up. So in this case you're going to heat them up, and hopefully one liquid will boil at a certain boiling point and the other liquid will boil at a slightly different boiling point. So you should be able to get them separate by just heating them up slowly. However, the problem with normal distillation is The distance that the gas has to travel is quite short, so what you'll generally end up with is both liquids end up boiling at a similar temperature, and they both go through the condenser at the same point and are not actually separated. With a fractional distillation setup, you've got a slightly longer passage for the gases to go through. This bit here is known as a fractionating column, and basically this makes it a little bit harder for a gas to get from the liquid at the start to the condenser at the end, and allows you to separate out your two liquids a little bit better, or two gases, before they go in and turn back into liquids, and get you a little bit better separation to get two different parts to your mixture separate from each other. The final technique you encounter for separating techniques is known as chromatography, and that's where you've got a mixture of soluble substances you want to get separate from each other. A good example of that would be a number of inks mixed together you might get from a pen, and want to see their individual components in this experiment. So how this works is you get a piece of chromatography paper, and you draw a line in pencil along the bottom of it with an X. That's known as your baseline or the origin. You then dip that piece of chromatography paper into a beaker of a solution of a solvent, which normally is something like water. The water will soak its way up through the paper, so you have to make sure the water level is below the origin, otherwise it all gets washed off. And as it gets soaked through the paper, the different components of the mixture, for example ink, will be pulled up the paper towards the top. The distance that the solvent gets to at the top, so how far it soaks through the paper, is known as the solvent front. And that can be useful for a little calculation to work out a key value for a substance in the chromatography experiment called the RF value. We'll look at in a second. Couple of bits of terminology though from that experiment. You've got two phases, which are two kind of parts of the experiment you need to know about. Two key parts of the experiment are the stationary phase and the mobile phase. The stationary phase is a part of the experiment that doesn't move. In this case, that's the paper. The mobile phase is something that does move. In this case, that's the solvent, which in a lot of cases will be water. So if a particular spot on your chromatography paper is very attracted to the stationary phase, it's not going to go very far and actually stay near the bottom of the paper. If something's very attracted to the mobile phase, such as this spot here, it's attracted to the water as it's moving up through the paper, and it's going to go very far in the experiment. So it's all to do with how attracted you are to the stationary phase versus the mobile phase. Now, a value you can be asked to calculate for a substance in the chromatography experiment is known as the RF value. The RF is a little fraction you can do, and it's the distance travelled by a substance divided by the distance travelled by the solvent in the same experiment. So if I look in this example here, the distance travelled by the substance is from the origin up to the spot, so that distance from the start of the X to the middle of that dot here. The distance travelled by the solvent is the distance from the origin up to the solvent front. So I'd take my ruler, I'd measure those two values and put them into the sum, and then end up with a decimal. Should be less than 1 because your spot should be travelling further than your solvent front. So a number that can be anything from like 0.1 to 0.9, and you just write down as a decimal value as an answer. The final part of the topic is some chemical tests you can carry out to identify unknown substances. There's only a couple of tests you're meant to know about in double awards, so let's go through them now. The first test for water. So if you've got a colourless liquid that you think might be water and you want to test it, you would take some anhydrous copper 2 sulfate, which is a powder you get from the chemical cupboard. It's a white colour when it's got no water attached to it, and anhydrous. When you add water to it, it turns into hydrated copper 2 sulfate, which has got a blue colour. So you see that white to blue colour change confirms you've got water. The second test you have to know about is the flame test. A flame test is used to test compounds, and to test them for one specific part of the compound, which is the metal ion. So if you've got a metal joined to non-metal, we're testing for the metal here. Basically what you do is you put the compound into a Bunsen burner flame, and you'll see a distinctive colour change of that flame to tell you what metal is there. So first thing is you need a little technique about how you actually do that test. You use a piece of equipment called a nichrome wire, which is basically a very kind of thin wire. It's made of a metal that doesn't have its own flame colour, makes it easy to see the flame colour you're looking for. You're going to clean it first by dipping into some concentrated hydrochloric acid and then into a Bunsen burner flame. And that's just to remove any impurities you might have from the last time you did the experiment. Once you got a clean wire, you're going to dip it into acid again to make it wet, to get your compound to stick to it, then dipping it into your compound. Then you place it in the blue Bunsen burner flame. Blue, because it's got a very faint colour, allows you to see your colour a bit more clearly, and you'll observe the same colour. There are 5 metals that you're meant to know their colours for, and you just have to learn it off by heart. If lithium's in the compound, you get a crimson flame colour. If sodium's in the compound, you either say yellow or orange. You can pick whatever one you want. For potassium, it's going to be a lilac flame colour. For calcium, it's going to be brick red. And for copper, it's going to be blue-green. And you just have to learn those off by heart as the flame colours.